Welcome back to this class on electronics testing. So, when we started the class, we talked about the importance of electronics testing. Then we have been discussing different fault models. Right. So, we talked about single circuit fault models, bridge fault models. Then we talked about speed testing. So, in speed testing, we talk about what is called as path delay faults. And I believe we looked at it last time, right. So, we have a sequential circuit, right. It has many state inputs. So, this is the next state and this is the previous state, primary inputs, primary outputs. So, for the synchronous sequential circuit to work correctly, right, when the clock comes, right, if this is T to Q, okay, when the clock comes, this D has to get captured in Q, and then there may be a path between this output Q all the way up to the next input D, right, and that path must get settled before the setup delay of, right. So, this is a clock to Q delay, right, and this is a setup delay. So, all paths must settle down in this much time. So, this is equal to T minus T clock to Q minus T setup, and if this constraint fails, then the sequential circuit will not update correctly, the state will not be updated correctly, and it will exhibit a failure, right. So, a path relay fault means we have to look at all possible paths, look at every path in the circuit from input to output, and ensure that the constraint the time constraint is met. Okay. So, this is a timing constraint T minus T clock to Q minus T setup. Now, how do we do that? I mean, so the path may look like this. So, this may be my path. Let me put it in a color. So, this is my path. So, let us say this is the the Q output of a flop, and this is the D input to another flop. Okay. And we want to ensure that this constraint is satisfied here. So, what we have to do is we have to make this wire, I mean this Q go from, let us say, 0 to 1, okay, and we have to make sure that this transition goes all the way. Okay. So, if I am able to put a 1 here, this will go from high to low, and if I can make this 0 somehow, this will go from low to high. If I can make this 0 somehow, this output will go from high to low, and if I can make this 0 somehow, this will go from low to high, and if I make this 1 somehow, this will go from low to high. So, I must somehow manage to put a transition on Q. Okay, this, let us say it is this flop. Okay, that transition will travel all the way and come here. Okay, and we must set all the inputs to these other gates in the uh, path such that the transition passes. Okay. If I put a 1 here, for example, the transition will not pass. If I make it a 1, this will become 0. If I make this 0, it will become 1 here. So, the this is known as a transition. Okay, it could be a rising transition or a falling transition. So, the rising transition or the falling transition must be able to propagate along this path and get captured here. Okay. So, that means so if I look at the combinational part, so these are the Q inputs coming and these are the D inputs and the D outputs. These may be some primary inputs and primary outputs. So, there will be many paths. Okay. So, if I have let us show a small example. So, if I call this A, B, C, D, okay, then E, F, G, H, I, J, K. Then from A to K, we have this path. Let me call this L. So, A, L, K is one path. Then A, E, G, H, J, K is another path. Then B, E, G, H, J, K is another path. Then C, F, G, H, J, K is another path. Then C, F, G, H, sorry, I, I didn't give it a name, no? L, I, L, K, that is another path. Then D, F, G, I, L, K. and finally DMLK. So you can see there are many paths even in this simple circuit. So you can imagine in a large circuit, the number of paths can be very large. Just out of sort of curiosity, you can try something like this. So just you can see how many paths there are, right? See, there are, if I have something like this, right? Take this guy. There are two ways it can propagate here, and then there are two ways it can propagate here, and then there are two ways it can propagate here. So from this input to this output, there are 8 paths. Okay, so I can go like this, and like this. That is one path. Then I can go like this and like this and like this. So there are 8 paths here. So if I end up with these kind of convergent fan outs like this, the number of paths will go up. Okay, these convergent fan outs, like things are converging here and then again they are branching out. These guys cause a lot of problems. They increase the number of paths. See, from E I can go like this, then I can go like this, I can go like this, I can go like this. There are 4 paths right there. So that is why the number of paths tend to increase. So actually the conclusion that we can draw is that path relay fault testing is a big challenge. We may not be able to do any justice to it because the number of paths is so large that it is very difficult to. Okay. Now, if I do take this circuit with many Q1, Q2, Q3, etc., and D1, D2, D3, etc., and primary inputs and primary outputs. So there could be a path like this. And like I mentioned earlier, we have to somehow cause a transition here, a rising transition maybe, and then also a falling transition, both. So just like we had stuck at 0 and stuck at 1, we can identify a path which is too slow to take the rising transition. Okay. Path P is too slow in transporting the rising transition. Suppose we write it like P. It could also be that path P is too slow in transporting the falling transition. Okay, we can write it like this. So, given that the number of parts is very large, okay, it may be in the order of several millions in a big circuit, we have to multiply it by 2 because we have to also worry about rising and falling transitions. So, the fault list, path delay fault list is too large. So, what is done instead is we simplify and create what is called as a transition delay fault model. So, it is very similar to how we started with multiple stuck-at faults and then argued that let us not do multiple stuck-at fault model, instead let us do only the single stuck-at fault model. In the same way, what we will do is, if there is a path like this, instead of looking at the entire path, we will say, look, there are these wires. Okay, let us call this wire x, x1, x2, x3, x4, etc. So, this is a full path. We can say that x0 is too slow to rise, or x0 is too slow to fall. So, we can write it as x0 and x0. So, this is a fault. Similarly, we can look at x1 too slow to rise, x2 too slow to fall, and so on. And we will assume that only one of them exists. Okay. The trick is, assume that only one node in the entire circuit has a slow to rise or a slow to fall fault. The rest of the nodes are good, they do not have any fault, and all the delay fault is concentrated at one particular node, either x0 or x1 or x2 or x3. So, that allows us to look at only all the nodes and say each node can be stuck at 0 or stuck at 1. So, now we are not looking at the number of paths, because the number of paths is very large, whereas the number of nodes is manageable. See, just like in the multiple stuck at faults, the number of faults can be exponentially large in terms of the number of nodes, whereas when we do single stuck at fault model, each node can be either stuck at 0 or stuck at 1. So, it is linear in terms of the number of nodes. In the same way, the number of transition delay faults is linear in terms of the number of nodes. So, the number of transition delay faults is twice the number of nodes, which is still very large, but can be manageable. It is not exponential. So, that is what is a simplification done. So, most people follow the transition delay fault model. We know that it is a big approximation. The right thing to do is to take path delay faults, but because it is very difficult to practice, people will do transition delay fault testing and argue that if you have done a good job of transition delay fault testing, it is many path delay faults will also be caught. We can't say everything. Okay. See, there may be no transition delay fault which causes the node to fail. See, suppose the period of this clock is T. Okay. Let us say it is equal to 10 nanoseconds. Let us say T clock to Q delay is 1 nanosecond and T setup is also 1 nanosecond. Then effectively we have 8 nanoseconds. Okay. In the transition delay fault model, we will assume that one particular node has a very large delay which causes this constraint to fail. That the total delay from x0 to x4 should be less than 8 nanoseconds. Okay. So, 10 nanosecond minus 2 nanosecond is 8 nanoseconds. So, we are assuming that all the delay is concentrated here. We may know that this delay is 2 nanoseconds, this may be 1 nanosecond, this may be 1 nanosecond and this may be 1 nanosecond. So, totally we have 2 plus 1 3, 4 and 5. Okay. So, for the fault to occur, we are assuming that this may be let us say having additional 5 nanosecond delay that will cause the circuit to fail. That is very unlikely. On the other hand, it is very likely that this node has 2 nanosecond delay additional, this may have another 2 nanosecond delay additional, this may have 1 nanosecond delay additional and this may have 1 nanosecond additional. So, all together they will cause the thing to fail. That is a path delay fault. But since we are not, it is not easy to test for path delay faults, we will assume that all the the extra delay is coming from one particular node. Okay. As you can realize, this is not realistic, not possible. Okay. But that is better than not doing any speed testing. Okay. It is better than not doing any speed testing. So, transition delay faults are slightly better than not doing any path delay fault testing.